I want to explain the relationship between the set pi0 of path components of K and the homology group H0. So here's the theorem. So for any abstract simplicial complex K, there's a natural isomorphism between the homology group H0K and the free abelian group with basis the set pi0 of the geometric realization of K. But recall we actually proved quite a while ago there was a sort of separate thing about the set of path components of the geometric realization. That's the same as this set pi0 abstract of K. So pi0 abstract of K, we take the set of vertices of K and we identify any two vertices. We declare them to be equivalent if there's an abstract path between them. In other words, a sequence of edges, one simplices in the simplicial complex with your first vertex at one end and the other one at the other end. Okay, so we proved that these two versions of pi0 are the same. And for this proof, it's going to work out to be most natural to work with the this pi0 abstract version. Okay. And so I say it's a natural isomorphism. I should mention that there's actually that word natural has a precise technical meaning in the sense of category theory. I'm not going to go through that here, but if you want to do some extra reading, you can check that out. To prove this, so we're going to let V be the set of vertices of K, and remember the zeroth chain group is just the free abelian group on V. Then we also have this this pi0 set. We're going to work with the abstract version, and the abstract version is just a quotient of V by an equivalence relation. And the equivalence relation is defined like this, that A is related to B if there's an abstract path, a sequence of edges starting from A and ending at B. Okay. So what we need to do is to identify the group H0K with a free abelian group on this quotient set V mod twiddle. So remember, H0K is Z0K mod B0K, so we need to understand those two things. And Z0K is the kernel of the D, which goes from C0K to C minus 1K, but C minus 1K is just 0, so that Z0K is just the same as C0K. So our H0K is just the quotient, C0K mod B0K. Okay. And okay, so what's B0K? So B0K is the image of our D1 from C1 down to C0. And so C1 is kind of generated by edges, and D1 of an edge AB is just B minus A. So, so our B0K is just the group generated by all these terms B minus A for all edges A and B of K. On the other hand, let's look at this this free abelian group generated by V mod twiddle. So that's the quotient of the free abelian group generated by V, in which we just identify any two basis elements A and B if they're related by this equivalence relation twiddle, which means we identify A with B if there's an abstract path between A and B. Okay. So notice, of course, that every edge in K, that counts as an abstract path just of length 1. Okay, and if you just take an abstract path of length 1, then the difference between the endpoints, B minus A, that's that's one of these terms of the second kind of the things that we're using to form this free abelian group on V mod twiddle. Okay, so in other words, the first type of terms, the D1 things, they're a subset of the second type of terms. On the other hand, suppose we've got one of these abstract paths for U, say from A to B. So that means that it's a sequence of vertices starting with U0 is A, and then U1, U2 up to UN minus 1, and then UN is B. Because for it to be an abstract path, that means that each adjacent pair UI plus 1 has got to be an edge. Okay, so so when we're forming this free abelian group on V mod twiddle, what we're doing is we're quotienting out by terms of the form B minus A for abstract paths like that. But the B minus A, you see, we can express as the sum of the terms UI minus 1. You take sort of U1 minus U0, U2 minus U1, etc. And we've seen this kind of telescopic cancelling before. Everything in the middle cancels out. And so you just, the sum of those UI minus 1s just ends up being the same as B minus A. Now, each of the terms in those sum, that's the difference of the two endpoints just of an edge. And difference in the two endpoints of an edge, that's our kind of first kind of terms. that we used when we were constructing H0K. So we see that the terms of the second kind, they can be expressed as a sum of terms of the first kind. So two different kinds of terms, they generate the same subgroup of the free abelian group on V. And so you've got the same subgroup and you take the quotients by those two different subgroups, except that they're really the same, and you get the same quotient. So one of those quotients was H0K, and the other quotient is the free abelian group on V mod twiddle. So those are the same as we claimed.